Assalamualaikum and hi everyone. So today our group will present about wave motion and sound. So this is our group members. In this chapter, we will cover 6 subtopics which are sound and ultrasound, generation of ultrasound wave, receiving ultrasound, what happened to ultrasound wave, ultrasound scanning mode and probe selection. Sound and ultrasound. What is sound? Sound is a vibration that is transmitted in a medium such as gas, liquid, or solid that can be heard by human. A normal human can hear sounds in the range of 20 Hz until 20 kHz. Human cannot hear infrasound which has frequency below 20 Hz and it is being used to monitor earthquakes and volcanoes. Ultrasound also cannot be heard by human as it has frequency above 20 kHz. Ultrasound is an imaging method that uses high-frequency sound waves to produce image of structures within our body. Advantages of ultrasound in medical diagnostic imaging. Ultrasound can be directed in a beam and it obeys the laws of reflection and refraction. Ultrasound also reflected off of small objects and brings no injuries to health. Principal disadvantages of ultrasound. Ultrasound propagates poorly through a gaseous medium as ultrasound transducer must have airless contact with the body during examination. Ultrasound images are relatively noisy and have poorer contrast than X-ray and MR modalities. Sound wave, also called as acoustic wave. Sound waves are an organized vibrations of the molecules of a medium that is able to support the propagation of these waves. It causes the molecules to move back and forth from their equilibrium position. The movement of molecules determines the frequency and amplitude of a sound. Sinusoidal sound wave is actually a series of areas of compression and rarefaction. Sine wave with the peak representing pressure maximum and valley representing pressure minimum. The combination of one compression and one rarefaction represent one cycle. The distance between the two of the peaks or valley is called as wavelength. The wavelength or lambda of the sound wave can be calculated in meter using formula lambda equal to 2 pi over k. K is the wave number. The velocity or the speed at which sound waves travel through a particular medium can be calculated using formula C equal to omega over k or 2 pi f over k. Omega and f represent the frequency of the energy delivered to the tissue. The speed of the sound and phase velocity can be calculated by using C equal to lambda f. The higher the frequency, the shorter the wavelength as both of them are inversely related. The speed of sound in a medium depends on the average density, ρ0, and the compressibility, K, of the material. The relationship is given by C equal to 1 over square root of ρ0 K. It is a convenient way to express relevant tissue properties by using the characteristic impedance which is defined by Z equal to ρ0.
For the second subtopic in this chapter, I will explain about generation of ultrasound wave. What is generation of ultrasound wave? Ultrasound waves are generated by a transducer that include a piezoelectric crystal that convert electrical energy, which is electric current, to mechanical energy, as we call as sound wave. These sound waves are reflected and returned to the transducer as echoes and converted back to electrical signal by the same transducer or by a separate one. Let me explain about meaning of piezoelectric. Piezo is stand for pressure. So that piezoelectric is that pressure is generated when electrical energy is applied to the crystal. How exactly piezoelectric works? Piezoelectric works when electric energy is applied to the face of the crystal. Then the shape of the crystal is changes or expand as a function of the polarity of the applied electrical energy. When the crystal expands and contracts, it produces compression and refraction and corresponding sound wave. Piezoelectric also can be used in medical imaging, but how it works? When an electric current is applied to piezoelectric crystal, it starts to vibrate. This vibration generates sound wave with between 1.5 and 8 MHz, which is ultrasound. Piezoelectric also can convert from electric current into ultrasound wave. crystal can do the opposite way, which is when the crystal are hit by reflected ultrasound wave, it starts to vibrate. Then mechanical vibrations are converted into electric current, which they're sent back to the ultrasound machine. Also, the electric signal is interpreted and translated into image. So for example, based on the picture, a piezoelectric crystal vibrates when an electric signal is applied, producing high frequency sound pressure wave, which we call as ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signal when it detects high frequency sound pressure wave. When a transducer detects ultrasound wave into the body, they pass right through the screen. As the wave encounter tissue with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal, as shown at picture number 2. So lastly, effect of high-frequency sinusoidal electrical stimulation is divided in three. First, on piezoelectric crystal, causing the crystal to vibrate. Second, to reduce a sinusoidal vibration. Third, they send through the conducting medium.
Next slide is receiving ultrasound. Ultrasound waves are produced by a transducer which can both emit ultrasound waves as well as detect the ultrasound echoes reflected back. In most cases, the active elements in ultrasound transducers are made of special ceramic crystal materials called piezoelectrics. Piezoelectric crystals have another very useful property that enables it to be also used for receiving ultrasound waves. Do you know how piezoelectric crystal works? When a piezoelectric crystal is compressed, it generates a voltage. This property is used to listen for the ultrasound waves that return after striking objects. When returning sound waves hit the piezoelectric crystal, it gets compressed. The crystal then generates a voltage that corresponds to the intensity of the ultrasound wave that hits it. The ultrasound machine conveniently uses the same piezoelectric crystal to transmit and to listen to ultrasound waves. First, the machine applies a voltage to the crystal to expand it and transmit. The ultrasound machine then very quickly switches to a listening mode by monitoring the voltage across the piezoelectric crystal. This transmit and receive cycle is repeated very rapidly. The above examples show only one crystal for clarity. In reality, ultrasound probes are composed of a large number of individual piezoelectric crystals. The information gathered from the crystals are processed by a computer to display the images on a screen. If you want to know, air is the enemy of ultrasound. Ultrasound waves tend to reflect strongly wherever air meets biological tissue. If there is even a small bubble between the probe and the patient's skin, the ultrasound waves will be reflected away instead of penetrating the skin. Without the waves going into the patient, you will not able to get a decent image. Therefore, it is absolutely vital to make sure that there are no air bubbles between the probe and the skin of the patient. Last but not least, ultrasound travels very easily through liquids. It is common to use a thick liquid jelly between the probe and the patient's skin. The thick liquid helps to keep away air bubbles and allows easy passage of the ultrasound waves.
Next is what happened to ultrasound wave. Some of the ultrasounds returns back to the probe once it enters the body to help the machine from an image while the rest is lost. It undergoes attenuation, refraction, and reflection when it enters the body. Attenuation is a loss of energy expressed as change in intensity measured as watts per square centimeter as the energy travels through a medium. Next is refraction. It occurs when an ultrasound wave tries to pass from one substance to another substance with a different acoustic impedance. And lastly is reflection. It means that scattered reflection happens when a small portion of the wave are reflected back to the probe. So here we want to look up what happens during attenuation. When the ultrasound waves are attenuated, this is when the body absorbs the ultrasound's energy, making the wave disappear. These waves don't return to the probe and be wasted. When attenuation wave suffer is high, the more body tissues that the ultrasound wave have to cross. That is why it is more difficult to image deeper structures. Decibels are used to express difference between ultrasound intensities. Rate of attenuation is called attenuation coefficient. Attenuation coefficient is half the frequency per cm for soft tissues. Every substance like nerves, muscles, or fat has a unique property called acoustic impedance. It is depends on the density and the speed of ultrasound in that substance. Substances with different acoustic impedances alter the course of ultrasound waves in an important manner. Next is refraction. It is occurs when the ultrasound signal is deflected from a straight path and the angle of the deflection is away from the transducer. Ultrasound waves are only refracted at a different medium interface of different acoustic impedance. Refraction allows enhanced image quality by using acoustic lenses. And lastly, the reflection. Irregular surface objects such as nerves scatter the ultrasound waves in all directions. More the difference of acoustic impedance, more the reflection, because the amount reflected back depends on the difference of the acoustic impedance between the two substances. As the ultrasound wave crosses from one tissue to the next, each with a different acoustic impedance, some of the wave is reflected back at each crossing. If an object is large and smooth like a nerve-blocking needle, all the ultrasound wave is reflected back. This is very useful since it helps us to clearly see needles when performing ultrasound-guided nerve blocks. This mirror-like reflection, when the waves are reflected back mostly in one direction, is officially called specular reflection. In this picture, red arrow shown the bending away when ultrasound tries to pass from one substance to another substance with a different acoustic impedance, which is called attenuation. The purple arrow shown ultrasound slightly bent away from original direction. The bending away when ultrasound passes from one substance to another substance with a different acoustic impedance is called refraction. And the blue arrow shown, the part of the wave is reflected back to the probe, which is reflected waves. Reflected waves are extremely important since it is only these waves that return back to the probe and provide information for the machine to show an image. Multiple reflected waves return to the probe and the machine uses this information to display an image showing the different tissues. So here is the mechanism that happen. Ultrasound are used to detect cracks in metal blocks after sonic waves are allowed to pass through the metal block. The detectors here are used to detect the flaws which it get reflected from the floor portion.
Assalamualaikum. I am now going to present ultrasound scanning modes. In this subtopic, I am going to cover the definition, A mode scanning, which is amplitude mode, and B mode scanning, which is brightness mode. So for the definition, the mode scanning is referred to as how an ultrasound probes can look at things. So what is A mode scanning? A mode scanning is referred to as amplitude mode scanning. It is the simplest form of ultrasonic imaging and is not frequently used. It works by the ultrasound wave exits the probe and travels in a narrow and straight path. It is used to measure length, for example, the diameter of the eyeball. So, how does it work? Following the example of measuring the diameter of an eyeball, a probe is placed on one end of it. An ultrasound wave is sent from the probe while at the same time, a line which moves horizontally and represents time appears on the screen. When the wave reaches the first wall, it is reflected back to the probe and is recorded as a bump on the line. The stronger the reflected wave, the higher the height of the bump. The height represents the amplitude, hence why it is called A scan. The ultrasound wave continues traveling into the eye until it hits another wall that is at the back of the eye, or the furthest from the probe. Like the previous wave, some gets reflected back to the probe and another bump appears. The time difference between the two bumps represents the time interval for the waves to travel between the two walls. The longer the length, the longer the time difference. When the time interval and the speed of the ultrasound is known, the distance traveled by the wave between the two walls can be calculated, which gives us the diameter of the eyeball. As you can see, this is the graphical representation of a scan mode. B mode scanning, also known as brightness mode, is similar to A scan mode. It sends an ultrasound wave in a narrow path, but instead of a line appearing on the screen, a dot marks the period of time the moment the wave is released. The B represents brightness. So, how does it work? Using the previous example, which is the eyeball, a probe is placed on one end of the eyeball. When the wave is released and meets the first wall, some of it reflects back to the probe and is shown as a bright dot on the screen. The brightness of the dot represents the strength of the returning wave. Therefore, the brighter the dot, the stronger the wave. The wave continues traveling until it meets the wall at the back of the eye. Some of it is reflected back and is represented as a bright dot on the screen like the previous reflected wave. This scan mode can also be used to obtain a two-dimensional image of an object on the screen by scanning the object at different levels. It starts at the top of the object, producing its first scan line, which is kept on the screen. The process is then repeated at different levels of the object multiple times until a two-dimensional image of the object is produced on the screen. This process occurs very quickly and the image is drawn multiple times per second. Full description of this mode is real-time two-dimensional B-scan. 2D refers to how the image has the x-axis horizontal and y-axis vertical. As you can see, this is the graphical representation of B-scan mode. You can see that it's producing a 2D image on the screen.
My name is Puteri Rahana, and today I will talk about probe, a surgical instrument used for exploring a wound or part of the body. There are three types of probe, which is first linear, second curvilinear, and third is phase array. Linear give rectangular image, and both of curvilinear and phase array give pie-shaped image. Curvilinear have two types of imaging, which is first is transabdominal, second is endocavitary. Transabdominal have wider footprint with lower frequency, but endocavitary have tighter array with higher frequency. Linear probe using high frequency. It imaging superficial structure and vessel. It also called bivascular probe. For phase array, they use electronically steered beam and it for cardiac ultrasound. Linear probe are usually used for superficial imaging. The piezoelectric crystal arrangement is linear and produce sound wave in a straight line. It has a higher frequency, which is 5 to 13 MHz, which have a better resolution but less penetration. There are two types of imaging in linear probe, which is 2D imaging and 3D imaging. Both of them have a wide footprint, but central frequency for 2D imaging is 2.5 MHz to 12 MHz, and 3D imaging have a frequency of 7.5 MHz to 11 MHz. This is the example of ultrasound image for linear array probe. This is lung imaging using straight linear array probe. R are referred to rib, P are for pleural line, and the S is for rib shadow. Linear probe are usually used for imaging vascular access, musculoskeletal, appendicitis, ocular ultrasound, and lastly testicular. Crystal arrangement for curvilinear probe is curved surface, and the transducer is good for in-depth examination. The resolution will decrease when the depth is increased. It has a wide footprint and its central frequency is 2.5 MHz to 7.5 MHz, which allow them to have a greater penetration, but the resolution will be decreased. The footprints, frequency, and the application are depend on whether the product is for 2D imaging or 3D imaging. This is the example image of ultrasound imaging for buffalo using curvilinear probe. We usually use curvilinear probe for abdominal and pelvic application. It also useful in certain musculoskeletal evaluation and procedure. Endocavitary probe are specialized for internal examination. It was designed to fit in the specific body orifice. The shape can be elongated that allowed it to be inserted close to the anatomy that being evaluated. The endocavitary transducer are including endovaginal, endorectal, and endocavity transducer. It has a small footprint that have a frequency varies of 8 MHz to 13 MHz. Phase array probe have crystals that are grouped closely together. The timing of the electrical pulses that are applied to the crystal are varies and they are fired in an oscillating manner. The sound waves that are generated originate from a single point and fan outward, then creating a sector type image. They have a frequency of 2 to 8 MHz, but they usually operate at higher end, making them suitable for echocardiography. It also functions at lower frequency and very helpful for viewing the abdomen, pelvis, and for procedural guidance. Phase array probe are usually used for cardiac imaging, brain examination, abdominal examination, transabdominal imaging if linear probe are not suitable, and imaging between ribs.